online and I already knew everything, so I didn't watch any of the lectures because they were just a waste of time.
Mm-hmm.
All right, sorry guys, I keep getting kicked out of my computer. I think I'm having some difficulty with my internet. Hopefully we can finish this problem, okay? So, all right, sorry about that. All right, so the momentum final, you can see that now you have two parts. One is the 2m, right? 2m moving with v2 cosine theta 2 because I want the x direction. The other one is 1m is moving with v1 cosine theta 1, okay? Right, so only x direction. Now let's apply it in the y direction. P initial y equals P final y. It's going to be second equation. Initially, there's nothing in the y, so it's 0. And finally, 2m have v2 sine theta 2 in the y, right? It's going up. Now v1 is going to have a negative sign, v1 sine of theta 1, going pointing down. That's why the negative sign. Okay, so I got two equations. I can solve for the two unknowns, v1 and v2. So is a trick I'm going to do. I'm going to multiply equation 1 by sine theta 2 and minus equation 2 multiplied by cosine theta 1. Cosine of theta 2. Okay. So if I multiply everything by sine theta 2, I get 3m v naught sine theta 2 is equal to 2m v2 cosine theta 2 sine theta 2 plus m v1 cosine theta 1 sine theta 2. Okay, so this is this part. The second equation multiplied by cosine theta 2 becomes this. Sine theta 2 cosine theta 2 minus mv1 sine theta 1 cosine theta 2. So 1 and 2 combined, this plus, yep, plus together, you get 3m v naught sine theta 2. The neat thing of doing this is you're going to be able to cancel out this term, right? They have a sine theta 1. Oh, I'm sorry. Maybe I mixed up one of these. Oh, sorry, I actually minus, it's minus, instead of plus, I do minuses, okay? Minuses, minuses, minuses. So I'm able to cancel out these two terms because they're the exact same, leaving this term, okay? All right, so this one is mv1 cos theta 1 sine theta 2 minus sine theta 1 cosine theta 2. Okay, so that helps me solve for v1. v1 is going to be 3, m cancels, v naught sine theta 2 over cosine theta 1 sine theta 2 minus sine theta 1 cosine theta 2. So you can plug in the numbers at this point, you get 1.46 times v naught. Okay, and plug in into any of these equations, you can get v2. So v2 is going to be mv1 sine theta 1 over 2m sine theta 2, which is going to be 1.08 times v naught. Okay, so you can see I applied my conservation of momentum twice in x direction and y direction. Okay. All right. So this is all for what we're gonna do for conservation of momentum in 2D. For the time remaining, instead of doing that kinetic elastic collision problem, I will upload that for you to look at yourself. I want to do a review, sort of summarizing the general approach and thought process that we do for solving these type of problems, okay? So for collision problems, you always use conservation of momentum, okay? If your system has consists of A and B, So A and B together, initial momentum of them is equal to the final momentum of them. And when you have an elastic collision, you have one extra condition is the kinetic energy of your system and the kinetic energy of the system final should be equal. Right? So you have one extra condition. When it's perfectly inelastic, you have another condition is because of the objects are stick together, they have the same final velocity. Okay. For a conservation of energy type of problems, a lot of times these collision problems have a second part that use conservation of energy, right? So E final minus E initial equals E in minus E out. So again, remember to choose your system and define your initial and final state, right? The common types of energy a system can have has kinetic energy or gravitational potential energy or elastic potential energy. So if you want to use potential energy for the gravitational potential energy, you need to include Earth. If you want to use elastic potential energy, you need to include the spring. If you don't include them, and they have to come up in terms of the work done, in terms of the transfer. Okay, so even though, so energy conservation of energy and conservation of momentum, these two topics will be on our second midterm. Okay, after today, I won't see you for another week because next week is a spring break. So I want to announce the midterm. I don't want to wait until the week after next week to announce it. It's going to be April 14th. I'll talk a little more about that just now later, but the energy type of problems and momentum type of problems will be coming up on the second midterm. But you can see a lot of times one problem can use both approach, okay? So for conservation of energy problems, if you, instead of doing the potential energy of the gravity or the spring, you will you can choose your system to be the object by itself and exclude Earth and exclude spring. Now, if you exclude them, they become external force and they can do work, right? So work done by gravity is either positive or negative mgh. So they can be either input and output. So when you're dropping something, right, gravity does positive work, and that's an energy input because the object is speeding up. When something going up and gravity is slowing down, and that's an opposite gravity because it's slowing things down. So this will become an input, and this will become an output. And work done by spring. Now, again, if you exclude spring from the system, the work done by spring is K x dx becomes 1/2 K delta x squared. Okay, it has exact the same format as your elastic potential energy, but it can be positive or negative. It can be, sorry, it can be an energy input or an output. But when your spring launches something, you're making the object speeding it up. That's your energy, that will be your energy input. When you slow something down, like the train, right? You use a spring to stop a train at a train station, and that is an energy output because it's slowing down. Work done by friction is always an output, and that's friction times displacement, right? Friction will be mu times the normal force. Of course, it's not always mg. If you're on the incline, the normal force is mg cosine theta. So be a little bit careful when you need to modify these into your corresponding problems. Okay, so I just want to mention that before at the sort of an overall review for these two chapters. Okay, I did get a question for the midterm here. Someone asked, when will the study guide be out? I thought I put it up already. If not, for sure this week, but definitely before your spring break, I'll put out a practice exam if it is not out already. Now let me check. I have it on. Okay, it's not out yet, but I'll put it out this week, okay, before your spring break. Will it be cumulative? No, it will be just your conservation of momentum and conservation of energy topic. Okay, just those two topics, including work, of course, work and power and all of that. It will be the same as format as before. It will be on Blackboard. I consider we'll give you more time this time. Will be same amount of questions, 20 questions, will with a mix of multiple choice and a few calculation problems. Okay. So it will be on April 14th, which is not is a Thursday. So last time is a Tuesday. This time it will be a Thursday. Okay. All right. So I will put in the announcement on Blackboard later, along with the practice exams. Okay. If so, you know it's coming. If you do want to use some of your sprint break time to study for it, you can do that. And I will, of course, remind you again when we get closer to the actual date. Okay. All right. So I think my recording sort of somehow I had two recordings. I got cut off, and the first video already started converting. Maybe I'll get a second video. I may have to put both of them up. But that's all for today. The last bit of elastic equation. The elastic equation, note that you can also solve that problem using a center of the mass frame. It's very neat. It's very elegant, but it will not be on the exam. Okay, center of the mass frame is something you can look into yourself. I do have solutions post as well, but it's not going to be tested. Okay, so for this problem, as you look at my notes later, I did include solutions for the center of the mass frame, but it will not be tested. All right, any questions for our exam coming up? If not, I'll see you guys in a week. Any questions? Okay, so if you do have questions, feel free to email me during spring break. If you need a problem solved or some questions, just email me and I can get back to you. I'll see you on Tuesday after next week.
Thank you, Professor. Have a good spring break.
Thank you, Professor. Have a
Have a
good
great spring break.
Thank you.
Thank you, guys. Bye.